All right, we're going to look at optimization here. One big difference now is we're going to look at things often on restricted domains, sometimes on closed intervals, sometimes on open intervals, sometimes on open rays. First, start with the definition. A global / absolute maximum or minimum is the largest or smallest value a function achieves on the indicated domain. Now, deviating from our book and most other books, but to simplify things a little bit, we can define the endpoint of an interval where a function is defined to be always critical. And I'm going to use open or closed endpoints here. Now, if you set up things in a certain language, this actually is true. The way our book does it, it may or may not be true depending on how you read some things. But for this class, I'm always going to consider the endpoint of an interval to be critical at all times. It's a boundary. It's important. Consider it critical. Okay? Because you basically consider that the endpoint, the derivative breaks. Therefore, the derivative doesn't exist there. So as a quick example, f of x equals 3x squared minus 18x defined on the interval 1 to 5, closed and open. F prime of x is 6x minus 18. So from here, we get that 6x minus 18 equals 0, or that when x equals 3, that is definitely a critical point like we've seen before. But with this above mention, I would say the critical points for this function are 1, 3, and 5. Check the critical points you found via traditional methods, but also include every endpoint you see. Okay? Pretty straightforward? Good. Check. The extreme value theorem says if f of x is continuous on the interval a to b, then f achieves both a global / absolute maximum and global / absolute minimum on the interval a to b. So if I'm on a closed interval, both endpoints are closed, neither endpoint here is infinity, I'm guaranteed a biggest thing, I'm guaranteed a smallest thing. How to find global extrema. Step 1. Find all critical points. Use limits if endpoints are plus or minus infinity. Show an example of that later. 2, make a table with one column all critical points and the other column the function value at said points. Step 3, find the largest and smallest values in the function column. Step 4, if the associated critical point is in the domain, it is a global extrema. One little note here. Finding optimal, but not necessarily upper and lower bounds is an identical methodology but you focus on the function values alone, and step 4 is not necessary. I'll put that in quotation marks, the point being there that we're not going to worry whether it's in the domain or not, but you still have to make sure you say which one's the upper bound, which one's the lower bound. Okay?